Alrighty, good morning, Algebra 2 CP. This is period A6. This is Friday, May 29th. Hopefully you're having a fantastic day so far, and we're going to try to make it even better with a little bit of Algebra 2 this morning. Today, what I would like to do with you is I'd just like to continue our discussion on applications of rational equations. I really appreciate last time that you were willing to stay just a couple extra minutes so I could finish the explanation on the last problem. Today, since I don't have to really go through an introduction because I spent some time introducing the three problem types to you, I should be able to spend a lot more time breaking down and explaining in full detail how each of these problems works out. If you do have any questions, you can feel free to ask at any time. A couple of reminders: make sure that you fill out the attendance form on Google Classroom. Also, make sure that you get that PA done over the weekend if you haven't done so already. I think I received like 3 or 4 submissions already, but if you haven't gotten it done, please make sure you get it done. For seniors in here, it is the last assessment that you do have to complete. I believe we only have one resident senior in this class, but that's okay. Make sure you do complete it. It is due Sunday night, so I can grade it Monday, and we can have our last progress assessment next week and call it a day for Algebra 2. But again, just because we're approaching the end of our time together doesn't mean we're going to go out on a whimper. We're going to go out on a high note with applications of rationals this week, and then next week we'll do a little Algebra 2 recap. All right, so that's my plan of attack for you. I think that's all I have for announcements and such. So let's go ahead and dive right in, shall we? Starting with the very first problem. The first problem, remember last class, what we did is we went over 3 types of word problems that I introduced to you. There was a distance, rate, and time problem, a work done problem, and a solution and mixture problem. The distance, rate, and time problem involves really applications of physics, the formula that distance is equal to rate times time. And you've probably seen in physics first this little diagram that I know physics teachers like to do with the D on top and the R and T on the side there. And that's just to show that distance is equal to rate times time, or distance divided by rate is time, or distance divided by time is rate, right? You hopefully can see that the first problem falls into that category because it's just talking about the language of driving and distance and time and trying to figure out how fast something's going. So it should be pretty obvious which of the 3 problem types these word problems fall into. I don't feel like I need to tell you that. I don't need to tell you that this is a work done problem or this is a solution mixture problem. It should be pretty obvious. The second problem is a work done problem, again for the reasons that it's 2 or more people, things, machines, in this case animals, working together to accomplish a goal. In this case, 2 pandas are eating from a particular patch of bamboo. I couldn't think of a more satisfying goal than eating. And last but not least, on the back side of the page, we have a solution mixture problem. In solution mixture problems, what we want to do is we want to take a base mixture that's already given, mix it with something else, and produce a desired concentration, right? So you can see that we currently have in this problem 40% hydrogen peroxide. We want to find out how much of a 70% hydrogen peroxide should we mix with it to get to 50%. So there's some ratio that's going to make that work out. All right, but let's go ahead and start with the very first problem here. Again, it's a distance, rate, and time problem. Like I said, since I don't have to go through that introduction today, hopefully that will leave me with more time to break down and explain to you what's going on with these word problems. But if you do have any questions at any point, please make sure you ask. So with the very first problem, it says, it's a distance, rate, and time problem. It says, my sister and I left the house at the same time. I was driving to my friend's house, which was 24 miles away, and she was driving to work, which was 30 miles away. Assuming that she is driving 10 miles per hour faster than me, true story. I do have a sister. I love her dearly, but she does drive faster than me. I hope she stays safe. How fast do each of us drive if we reach our destinations at the same time? So it says, actually twice in the problem, that this is all happening within the same amount of time. We're leaving at the same time. We're arriving at the same time. So that means the total travel time of me, so I'm going to say my time, is the exact same as my sister's time, right? And if we're driving, how do you calculate time? Well, time, if you remember, based on our little formula up here, is distance divided by rate. So since we've established the fact that my time spent traveling is the same as her time spent traveling, that should make sense that my distance divided by my rate, because that's equal to time, should equal her distance divided by her rate, right? And now it's just a matter of filling in the information. So how far did I drive? Well, it says it right here. I drove 24 miles, and she drove 30 miles. It says it in the problem as well, right here. Assuming she is driving 10 miles per hour faster than me. Well, if she's going 10 miles per hour faster than me, how fast am I going? Well, the answer to that question is we don't know. We don't know how fast I'm going, but we can indicate that with an x. Okay, that's my rate. And if I'm traveling x miles per hour and she's going 10 miles per hour faster, well, then it would make sense to represent her rate as x plus 10. Does that make sense as to how that was done? Does anybody have a question as to how that was done? All right. Now we have just a typical rational equation that we could go ahead and solve. Our least common denominator here is x times x plus 10, right? I need a factor of x to make this happy. I need a factor of x plus 10 to make this happy. Yes? Now I can go ahead and convert all of my fractions. I'll continue my work right up here. I would like both of my denominators to look like this, x times x plus 10 and x times x plus 10. All right. What do I need to multiply this by in order to get this? Well, I'm missing the factor of x plus 10. So I'm going to take the 24 that's already in the numerator and multiply it by x plus 10. What do I need to do to this to make it look like this? Well, I'm missing the factor of x from here. So I'm going to take the 30 that's already in the numerator and multiply it by x. One thing I didn't mention that's coming into my head right now is I did type up these problems and post them on the Google Classroom page. So if you are struggling to read my handwritten work over here, you can look at the typed document and follow along in a separate tab if you desire. But anyway, now that the denominators match up, we can go ahead and disregard them and just focus on the numerators. We get a little distributing, 24x plus 240, that's if we multiply like this, is equal to 30x. And slightly bigger numbers than we may be used to, but this is still just a case of Algebra 1, where I can go ahead and subtract 24x from both sides. You get 240 is equal to 6x. Divide both sides by 6, and you're going to get that x is equal to 40. Okay? But what does that actually mean in the context of the problem? One thing that's very important with these word problems, and I find an area that students make a very common mistake, is they'll do all the hard work. They'll get x is equal to 40, and then they'll put a bubble, a cloud, a box around it, or highlight it, whatever they do, and stop and move on. X equals 40 doesn't really answer the question. The question here is asking, how fast do each of us drive if we reach our destination at the same time? So if I asked you that, how fast do each of us drive, and you would respond, x equals 40, that's not really a good answer to the question, right? So I want to make sure that I say that I drove 40 miles per hour because my rate was represented by x, and my sister drove 40 plus 10 miles per hour or 50 miles per hour. And that is really how you want to answer these types of applications. Any question about that at all? Distance, rate, and time problem. That's a typical distance, rate, and time problem. Feeling good about that? I take your silence as, yes, Mr. Giorgio, we're feeling fantastic, and you are doing a great job. Well, thank you so much. I appreciate it. All right, let's go ahead and move into problem 2. Problem 2 is a work done problem. It says, a panda can eat the stalks from a particular patch of bamboo in 15 minutes. Together, 2 pandas can eat the stalks from that same patch of bamboo in 9 minutes. How long would it have taken the second panda to eat the patch of bamboo stalks by itself? Well, what's happening here is 2 things are working together to accomplish a common goal, which is why it's a work done problem. What I want to do for each of the pandas is figure out its rate per unit of time and the time that each one contributed towards accomplishing the task. So I'm going to make a little chart to organize my data. We have the first panda, panda 1, and the second panda, panda 2. Panda is a top tier animal, by the way. We have its rate per, in this case, it looks like it's minute, right? Could be rate per day in another problem, rate per hour, rate per second. That's why it's referred to as rate per unit of time, but in this case, it's minute. and we're looking at their time contributed. Just like that, right? So let's try to organize our data, create an equation, and solve. The first panda, right? The first panda, it says it can eat the stalks from the bamboo in 15 minutes. So if it takes 15 minutes for this panda to eat the bamboo stalks, and the panda is working at a constant rate, how much of that stalk gets eaten per minute? And the answer to that is 1/15 of it. Right? If it takes 15 minutes to accomplish the whole task, then every minute, 1/15 of the task is getting done. So that's why we say the panda's rate per minute is 1/15 of the patch of bamboo per minute. Because after 15 minutes, it would have eaten the whole thing, 15 out of 15. The time contributed for both of these things is 9. If you notice, if they both work together, if they both contribute 9 minutes, they can both eat that same patch of bamboo together, right? The time contributed, by the way, is not always the same, but for our purposes in a distance learning environment, I don't think I'm going to present problems to you in which the time contributed is different, because that definitely involves a little trickier language. I decided to just keep everything very, very straightforward. The same thing can happen in a distance, rate, and time. You can certainly end up with some tricks thrown in there and some little twists and turns. Same thing in a solution mixture. But for our current setting, and I think under this, given the circumstances and our limited amount of time together, it's best to just keep everything straightforward. So I want to give you that essential information. So I'm pretty sure I can say confidently that for most of the time contributed will be the same. But think of it as if these things work together, if these things are working in tandem, how much time do each of them contribute before the goal is accomplished? And it says here that they both contribute 9 minutes and can eat that same patch. Okay. Now the unknown piece of information is panda 2. How long would it have taken the second panda to eat the stalks of bamboo by itself? Well, you're very tempted to say, just put an X here, right? Because we don't know. But think about it. If it takes X minutes for that panda to eat the patch of bamboo stalks, how much of that patch would get eaten per minute? And the answer to that is 1x, 1 over x. Think about it. If it took 5 minutes, then we would say that its rate per minute is 1/5. If it took 7 minutes, we would say its rate per minute is 1/7. If it takes x minutes, then its rate per minute is 1x, 1 over x. Does that make sense how we set up that information and how we extract that information from the problem? All right, not hearing any questions. We can then set up our equation to say, well, if the first panda is working at a rate of 1/15 of a patch of bamboo for 9 minutes, and, so plus, the second panda is working at a rate of 1x of a bamboo patch for 9 minutes, then together they consume one entire patch of bamboo. So that's why we set up our equation that way. It translates very literally from a spoken sentence, and that's why it works out. All right. Now I can go ahead and solve this equation by multiplying. I get here 9 over 15. That's 1 over 15 times 9. Plus 9 over x is equal to 1. This is a typical rational equation that we've worked to solve. The least common denominator here is 15x. I need a factor of 15, and I need a factor of x. Now, the most common mistake that students make with these types of problems is forgetting to convert the 1. Please, please, please do not forget to convert this extra floating 1 over here. The least common denominator is 15x. We need to convert all 3 denominators. 15x here, 15x here, 15x here. Okay? What do I need to multiply this by in order to get this? I need to multiply by x. So I'm going to take the 9 that's already there, multiply by x. What do I need to multiply this by to get this? I need to multiply by the 15. 9 times 15. And what do I need to multiply this by to get this? It's the entirety of 15x. Again, please don't forget to convert that constant. Now I can go ahead and disregard my denominators, just focus on the numerators. I get 9x plus 9 times 15. Rats. I think I was going to say 135. Of course you're like, of course he was going to say 135. Just showed out with a calculator. whatever. 9x plus 135 is equal to 15. Subtract 9x on both sides. This is algebra 1 at this point. We get 135 is equal to 6x. And I don't think this is going to be an integer, but let's see. 135 divided by 6, we get 22.5. Which means that it would have taken the second panda 22.5 minutes, or 22 minutes and 30 seconds, to eat the patch of bamboo alone. Slower eater than his friend. Any questions about how that was done? Sean, thank you. He says, nope, we're all clear over here. We're all good. All right, fantastic. Happy to hear it. Let's go ahead and jump to our third problem then. Last one of the day. All right, this is a solution and mixture problem. It states, a bottle currently holds 750 milliliters of a solution that is 40% hydrogen peroxide. How much of a 70% hydrogen peroxide solution should be added to obtain a solution that is 50% hydrogen peroxide? So what's going on here is I have my first mixture, which is my 40% hydrogen peroxide solution. I'm going to combine that with my second mixture, which is the 70% hydrogen peroxide solution, and I want that to equal the final mixture, which is the 50% hydrogen peroxide. So I set it up like this because the two pieces of information I'm going to keep track of are the volume of the solution, or the amount, if you prefer, and the concentration. Fancy word for the percentage. Okay? So I look here and it says a bottle currently holds 750 milliliters of a solution that is 40% hydrogen peroxide. So I'm starting with 750 milliliters of a solution that's 40% hydrogen peroxide. 40%, how do I represent that as a fraction? Well, I could represent that as 40 over 100. I'm also going to intentionally not reduce the fraction. Yes, you could reduce it to 4/10 or 2/5, but I'm intentionally not going to do that because you're going to see later on, if we don't reduce all the fractions, all your denominators are already common and we're able to just eliminate them. If you reduce the denominators, then you almost have to unreduce them, if that makes sense, to get a common denominator and go from there. So it just saves us a little bit of work if we just leave that alone, 40 over 100. And we can rest assured that the denominators will line up because we're all talking in percentages, so they're all going to be out of 100. It then says, going forward, how much of a 70% hydrogen peroxide solution? So we don't know how much of this solution should be added, so we're going to put an X. We don't know how much that should be, but we do know it's 70%. Should be added to obtain a solution that's 50% hydrogen peroxide. So we want to get a 50% hydrogen peroxide solution. And now the question is, how much of that solution will there be? A lot of students are when I present this in class, a lot of students are very tempted to put an extra variable here, and they say, do we call that y? You certainly could do that, but then it would require solving a system of equations. It would make it a whole lot harder. Much, much easier to just think about the fact that if I'm mixing 750 milliliters of this and combining that with X milliliters of this, then how many milliliters are going to be in your final solution? It's going to be the two combined together. It's going to be 750 plus X. Does that make sense to everybody, why that's the case? Hopefully it does. Hopefully we're feeling good. Okay. Again, Zach, he's like, yes. Yes, sir. All right, I like to hear it. So now I can go ahead and set up my equation here, and I could say we have 750 milliliters of a 40% solution. So 750 milliliters times my 40% plus X milliliters of a 70% solution, because I'm combining this with this, so we're adding them together. And that should result in 750 plus X milliliters of a 50% solution. Okay? We want to figure out for what value that makes that true. I can go ahead and multiply now. We're going to need our handy dandy calculator again. I have 750 times 40. That's going to come out to be 30,000 over 100 plus 70x over 100 is equal to, just a little bit of distributing here, I'm going to get 750 times 50. 750 times 50 is going to be 37,500 plus 50x all over 100. And although the numbers are larger than you may be used to seeing in a typical algebra problem, the great benefit that happens here is you notice all of your denominators are already the same. They're all out of 100, meaning that they already match. They already have the least common denominator, so we can just focus on the numerator and say 30,000 plus 70x is equal to 37,500 plus 50x. And once again, this now turns into Algebra 1. Big numbers, but still Algebra 1. I'm going to get all the variables on one side, all the constants on the other side. Does anybody have a question before I finish up this problem? All right, let's do it. So I'm going to subtract 50x from both sides. I'm going to also subtract 30,000 from both sides. That gives me 20x is equal to, let's see, 7,500. Divide both sides by 20, and I'm going to get 7,500 divided by 20, 375 milliliters. Which means that I should add 375 milliliters of this 70% hydrogen peroxide solution to obtain my final mixture, which would be, if my mental math is correct, 1,125 milliliters in total. Right? Not that the problem asks you for that, but if it did, if it said how much will I end up with, then certainly you could answer that as well by noticing that we're just taking our 750 here, our 375 here, and mixing them together. Alrighty. Does anybody have a question or comment or concern about this problem? Looks like we're feeling good. So, quick little recap. What we did today is we went over one of each type of problem. Like I mentioned, given the current learning environment, I am not inclined to put in twists and turns and all sorts of the variations that can happen in problems like these. I'm just sticking with very, very straightforward examples, and that's exactly what you can see on assessments because I think it's important for you to get the essential information. So any distance, rate, and time problem, you just want to go ahead and establish which of the which of the three factors, distance, rate, or time, are equal to each other. From there, you can then build your equation and plug in what you need and solve. In a work done problem, we can figure out the rate per minute or rate per day or rate per hour, whatever the specific problem happens to be, the time contributed here, and we can figure out this one's rate per minute as well. And in our third problem, we did a solution mixture problem where we figure out the amount and the concentration for each, and we understand that we're mixing these two together to create this one, so that's why we can just add them together. Okay? One other reminder, I want to make sure you guys go ahead and complete that PA this weekend. Please make sure you get that done. It's only 4 problems this time. Normally it's been 4. So it's 4 problems, only 3 word problems though, 1 equation and 3 word problems. So make sure you get that done. Please submit it to me by Sunday night. Would extend a congratulations to our resident senior in this class for making it through Algebra 2, but our resident senior is not present. So if the resident senior happens to watch the recording, then congratulations and best of luck in the future. And for everybody else, we'll get a little sentimental next week when we reach the conclusion of our scheduled Algebra 2 time together. But until then, we're going to end off next week on a high note. Thank you so much for your attention and focus today. I hope you have a fantastic rest of your day, and I hope you have a great weekend. Bye, everyone. Sean, you have a good day as well.
Thank you.
See you later. Have a great day.